Greetings! This is the second part of first chapter. In this video, you will learn about the most important metrics in computer architecture, which are used for evaluation of different architectures and or processes. In this part, we will cover performance, power and energy consumption, utilization, and area overhead. We start with performance. Performance of an system is a metric that shows how well it works or performs a specific work. It gets very important when we want to buy something. We always like to choose the best option with our available budget. For example, we have $500 and we want to have the fastest processor in this price range. These days, assessing the performance of computers is quite challenging due to the scale of modern software and wide range of performance improvement techniques employed by hardware designers. For example, if computer architects design a new architecture that uses directions from higher levels like operating system, and operating system does optimizations according to the lower levels information, it will affect the performance evaluation process. They have to consider how their new proposal fits the number of instructions required to be executed. For example, how cache miss and hit rate will be affected. Performance definition differs from a computer to another one. For example, for PC, response or execution time is considered as the metric. It shows how fast a program is executed by a PC computer. However, for a server, throughput or bandwidth is considered as performance. In other words, the number of tasks done in a unit of time, a second, is considered in this one. So, how to improve performance? We can get high performance easily by replacing a processor with a faster one or adding more processors. The first one is usually achieved by technology advancements, and the latter one is attained by parallelism, parallel processing. Usually processor vendors tend to report numbers like the processor clock frequency or clock rate to misguide buyers on their purchase. But these numbers say nearly nothing about the performance of processes. Look at this example. We have two processes, one with 4 GHz clock frequency and another one with 3.8 GHz. But these numbers just show the frequency of the clock, nothing more. A simple definition of performance is related to the execution time as shown in the formula. It means as less the execution time is, higher the performance is, and CPU performance is the time spent by the processor to execute a program. And clock frequency cannot be used for comparing processes. So how can we compare two processes? The answer is simple. If we run the same program on both of them, we will be able to compare them fairly. It looks like a contest. The processor which finishes the program earlier is a better one, or its performance is higher than the other one. We usually call that program a benchmark. Benchmarks can be categorized into different groups like collections of real applications, like what we have in ISPEC benchmark suite. Synthetic programs which are testing some specific part of a processor like ILU units, or kernel loops like quicksort and matrix multiplication. Let's see an example from Patterson's book. Computer A finishes the program in 10 seconds and computer B finishes it in 15 seconds. The performance ratio of computer A to computer B is 1.5. It means that computer A is 1.5 times faster than computer A. Let's extend our formula. We said earlier that for comparing two processes, we can run a benchmark or a testing program on both of them. Here we want to calculate the execution time of that program for each specific process. We know that when our compiler translates the benchmark, it changes the high-level language instructions to our process instructions. These instructions take some clock cycles or clock ticks to be executed, and because we know the clock rate of the processor, so we have the execution time of the program on our processor. Let's change our equation in a way to have considered the number of instructions of the program. It's important because different processors with different ISAs have a different sequence of instructions for identical high-level program. This formula shows that the execution time of a program is affected by three parameters: instructions for program, average clocks per instruction or CPI, and clock cycle time. It can be used to compare two different implementations or to evaluate a design alternative on knowing its impact on these three parameters. This formula is known as Iron's law. Let's see an example from Patterson's book to better understand this formula. Example: a compiler design is trying to decide between two code sequences for a computer. So clock rate is same and no need to be considered in our equations. The hardware designers have supplied the following facts. The table shows CPI for each instruction class. For a particular high-level language statement, the compiler writer is considering two code sequences that require the following instruction counts. Each row of the second table shows how many instructions of each instruction class are required for each code sequence. Question number 1. Which code sequence executes the most instructions? To answer this question, we can easily sum the numbers of instructions of different classes required for each code sequence, which results show that sequence number 2 executes the most instructions. Question number 2. Which will be faster? Because both of the code sequences run on the same computer, clock rate is not required to be considered. If we calculate the number of CPU cycles for each code sequence, it will show us which sequence is faster. We can have the number of CPU cycles or ticks for each sequence by summing products of instructions counts and their corresponding CPIs, as shown in the figure. The results show that sequence number 2 is faster. Question number 3. What is the CPI for each sequence? CPI stands for clocks per instruction. From previous questions, we have the number of clocks and the number of instructions. We have the answer, so we have the answer by a single division. And note that sequence number 2 executes more instructions, but also it's faster. Let's see what impacts execution time for programs based on the Iron's law. So let's see what impacts each of these three factors. Number of instructions of a program is impacted by ISA and compiler. As the ISA consists of instruction sets plus other information required for programming a processor, it can indeed impact the number of instructions of a program. For example, consider a processor with a sign instruction in its ISA and another one without this instruction in its ISA. So if a programmer in his Python program does some sign calculations, after compiling the program for the process, the first one will use a single instruction from its ISA, but the second one should execute many arithmetic instructions usually generated by its compiler to do that computation. So different compilers can lead to different instruction sequences with different numbers of instructions based on their optimizations. CPI, or average clock per instruction, is affected by microarchitecture, compiler, and ISA. Microarchitecture is the implementation of the ISA or the instruction set and other specific details of the interface. For example, one architect implements an instruction in a way that it takes only 2 cycles to be executed. On the other hand, another architect implements it in a way that takes 3 cycles to be executed. Compiler, based on its selections of instructions from the ISA, affects the average CPI. You can see this in the previous example that we saw together. And ISA affects CPI by the type and number of instructions it supports. Remember the sign instruction. And clock rate is impacted by technology advancements and circuit optimizations. As technology advances, we see processes with higher clock frequencies due to the smaller sizes according to the Moore's law. Also, it's impacted by microarchitecture. Critical paths in logical digital circuits for implementing the ISA impact the clock cycle. And finally, ISA with its instruction set impact the clock rate. So now we know what performance is, but how do researchers evaluate their proposed architectures and mechanisms? They usually either use analytical models or software models. Analytical or mathematical models describe a system with mathematical language helping to explain the system and to study the effects of different components and also to make predictions about the system's behavior. For example, this paper, an analytical model for GPU architecture with memory level and thread level parallelism awareness, presents an analytical model to predict the performance of general purpose applications on a graphics processing unit. Also, there are many performance and power analytical models proposed in academia. You can go and find tons of them just by doing a simple Google search. The second and the most widely used approach of evaluating performance is using software models or doing simulation or simulating. In general, simulation is the imitation of the operation of a real-world process or system. There are many simulators for processors and memories like GEM5, which is an open source system level and process simulator, GPU-Sim, which is a cycle level GPU performance simulator, BookSim, a cycle accurate interconnection network simulator, and finally ZSim, which is a x86-64 processor simulator. Power and energy consumption. Electrical energy is a kind of kinetic energy for moving electrons or making them to move from one place to another place. It's drawn from this energy is usually drawn from a voltage source, such as a battery. In this figure, you can see how electrons move within a circuit. Some electrons from the voltage source pushes other electrons to flow in a domino way in the circuit. Power. Power is the amount of energy transferred or converted in a single unit of time. In electronics, power is equal to the product of current and voltage. The figure above shows the power and energy difference clearly. We have power in just one moment of time, but energy is the sum of all of those powers in a time range. Consumed energy in logical digital circuits consists of dynamic and static energy. Static energy, sometimes it is called dissipated energy, is the energy wasted due to the leakage of electronic devices. Because these devices are non-ideal, they don't behave exactly like we have modeled them in the equations. And dynamic energy is considered as the primary source of energy consumption. Dynamic energy is consumed when transistors switch states from 1 to 0 and vice versa. The dynamic energy depends on the capacitive loading of each transistor, which is a function of the number of transistors connected to an output and the technology and the voltage applied. The equation is the energy of a pulse during the logic transition from 1 to 0, then from 1 to 0 or vice versa. So the energy of a single transition is half of what we have in this equation. On power, we know that power is the consumed energy in a unit of time, and frequency is the one divided by time. So for power, if we multiply clock rate to energy, we will have the power equation. According to this equation, if we decrease voltage, we will decrease energy consumption. However, note that at low voltages, transistors get more leaky, and the static energy consumption's portion on the total energy consumption increases, as 40% of today's server's energy consumption is due to leakage. One of the software tools that is widely used by computer architecture researchers for energy consumption evaluations is Watch. It is an architecture simulator estimating CPU power consumption. Its estimations are based on a suite of parameterizable power models for different hardware structures and on per cycle resource usage counts generated through cycle level simulation, for example from a simulator like Gen 5. Utilization refers to the usage of resources, specifically transistors. Always we want to fully use what we pay for. We can measure the utilization of a structure or architecture by analyzing the source code of benchmarks that we are going to run on processors to evaluate the performance of them, or simply using simulators. Let's assume a mechanism that needs 10,000 transistors, but 40% of the times it's not used at all, and in the remaining 60% only 20% of it is used. So it's too inefficient. These wasted transistors or resources can be used for other purposes, like to be managed in a better way to provide more performance. Area overhead. This metric shows the on-chip area imposed, and this shows the on-chip area overhead imposed by a mechanism or architecture or optimization technique. On-chip area is measured in square millimeters. Let's consider an example. A researcher proposed an optimization technique for the state-of-the-art cache memories, which improves these on-chip memories performance. Alongside with the proposed mechanism performance evaluations, the researcher should evaluate area overhead that his technique imposes. Additionally, he has to prove that performance gains of the proposed mechanism was the imposed area overhead and also other overheads like energy and power overheads. CAC type P tool is usually used for area and power overhead evaluations. Recommended reading material for this part is Chapter 1 from Computer Organization and Design, the Hardware-Software Interface book from David Patterson and John Hennessy. In addition to that chapter, further search and read about anything that looks vague for you and ask questions in the comments section. Also, I prepared some exercises with their solutions in separate files, and you can access them by the links in the description of this video. Just first of all, try to solve the exercises by yourself, then check the solutions. In the next video, you will have a quiz of this video's content for a review. Thank you for your time and attention.